The most common I/O addresses. So if any of you are well on your way to becoming BIOS engineers, you need to know all of these addresses, right? Everything's got specific addresses on the basic parts of the system. So the PC port 3F8 hex to 3FF hex. Remember we talked about binary to hex. These are hexadecimal numbers. That's what the little h signifies. That's COM1. That's the addressing space for COM1. And then 378 or 37F is LPT1. That's an old school printer port. And then we have C000 to C7FF. That's for the VGA port. 278 to 2FF, that's COM2. Okay? So 3F8 to 2F8. 3FF to 2FF. You see the symbology there? And then we have a 278 versus 378. That's LPT2, right? And then we have a floppy disk controller. 3F0 to 3F7, which we still support today, but it's done via USB. Setting and managing I/O addresses. Non-plug and play. So non-plug and play I/O addresses are set with jumpers, dual inline packet switches, and software drivers. So on the motherboard, there were two pins that would stick up in certain, I mean, they're all over the motherboard, and you had to configure whether you wanted on or off. So we had a little box that would slip over this that would short these two pins out. So it basically just connect the pins. That's all it would do. When you put the little box over it, it connects the pins. That's what they're trying to describe here. The DIP, the dual inline pin switches. So that's literally just a switch. But the jumpers, that's what they're talking about here. You have two pins that point straight up, and you basically put a little box over them. And then that would just basically short the pins. So they're surrounded by plastic, but on the inside they're just shorted, which means it's on or off. So you're telling it you want to enable or disable this thing, whether or not the jumper was set. And a lot of times, so let's say this is our block of pin shorter. So when we put this on, those pins are shorted, right? Basically on the inside, they're touching. So a lot of times it's just sitting off to the side, only hooked to one pin. So it's there in case you need it. You just pick it up and short both pins, right? That's kind of how it worked. So you would cover up one pin, but not both pins. So don't let that throw you if you get one of these old motherboards that has those on there. And there's plenty of reference and stuff for that. So that's how you used to erase the CMOS or clear the CMOS. That's how you used to do all kinds of things. Configuring hard drives, beeping or not, all this kind of stuff. So plug and play devices are self-configuring and can conflict with older non-plug and play cards. This used to be a problem. Today, everything's plug and play. You don't have to worry about this. Again, this is in really old computers. You probably will not see these, and if you do, you're probably replacing it anyway. Devices with overlapping I/O addresses will not respond to commands. So something where the memory is overlapped, they won't respond because the commands in there, the ones and zeros they're seeing are all messed up. It doesn't mean anything. It's not something that they understand, so they'll just quit responding. You get you get junk in, you get junk out, right? With a computer, junk in, junk out. So an IRQ, what is an IRQ? So there's two types of monitoring, and there's interrupt driven and there's polling. So we're talking about interrupt driven here, interrupt requests, IRQs. So let's think of a keyboard. And I'm going to press, Tim, T-I-M, T-I-M. So when I do that, the computer is, are you pressing the key? 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 But it's not only doing that, it's looking at, are you pressing key 1? Are you pressing key 2? Are you pressing key 3? For every single key, over and over and over and over and over like that. That's what it's doing. It's looking, is it pressed? Is it pressed? Is it pressed? Is it pressed? But it's doing it very, 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 very fast. That's polling. It's just checking, 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 and it's polling faster than I can possibly type. That's how it's designed, right? So if you get a super speedy typist, it might miss a key because it's busy. Something happens and the computer missed a check. Maybe you miss the character and you got to backspace and then type it and then keep going, right? That can happen, especially on the first models. You had to type kind of deliberately. But nowadays, you don't have to do that at all. So that's polling. Now we're going to talk about what is interrupt driven. Nothing is happening. Everything's still and calm. You see how busy that thing was before. That's a lot of work, right? It's just sitting there working its butt off. But now it's just sitting back, relaxing and just waiting for somebody to press a key. So it's just sitting here relaxing. And then all of a sudden I go and I press T for Tim. Now that sends a signal and said, hey, key pressed. And then it tells you which key was pressed. So it sends it right to the processor, so the processor knows, oh, I get a T. Okay, do I need to wait for something else, or are we going back to sleep, right? So that's what it's going to do. So that's the difference between interrupt request. It's going to tell the processor, hey, key pressed, and it was a T, versus the CPU going, did you press a key, did you press a key, did you press a key? So that's how it works. And polling, typically, we're talking about, with interrupts, generally we're talking about the CPU itself. So it might be something more critical, like a read or write, or hey, I finished putting that memory up there that you asked for. Here's this, you send a signal to say, hey, it's done. But you see right here, number 1, that's a keyboard interrupt request. So that means the key was pressed, right? So you may have a chip down here just pulling the keyboard, and then it'll send the interrupt. Or it could, the whole keyboard could be interrupt driven only. So we have interrupts for the system timer. So if I set a timer, like an alarm, and it's counting down, when the system timer goes, it'll tell me that it's going off. Or it could be just tick, 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 tick. It's telling me that a tick went by for the crystal. So that was a microsecond in time, or a flash of a microsecond, something like that, whatever it's set up to. And then we have a keyboard, which we talked about that. As you press a key, it sends an interrupt. And then that one's reserved. And then we have serial devices. So if I have a serial device that's doing something like, say I have a cell phone hooked up to it and it rings, it might send an interrupt. The mouse moves, it might send a signal, hey, the mouse is moving, that kind of thing. And then we have parallel devices like printers, like, hey, I'm finished printing. Here's your signal. I'm finished printing what you gave me to print. And then it might pop up, you know, it might clear the screen, like your printer's sitting there sending data, sending data, sending data. All the data's sent, but it's still sitting there waiting to make sure it was successful. The printer says, I'm done, and it sends an interrupt back up, and it tells your program, hey, the print's done. Okay, great, thanks. And it goes away. And then it's ready to do something else. The word pops back up or whatever. And then you have floppy drives. If I insert a floppy disk, it might say, hey, floppy disk installed. Go ahead and auto-detect what's on the disk and show up in the My Computer window. And then we have some other parallel devices like scanners, all kinds of different stuff, right? So those are what interrupts are about, and there's a bunch of them in a computer.